Hi, everyone, and welcome to WOW 11 Day 2. Today's webinar, Machine Learning and Predictive Maintenance Solutions, Case Studies, Challenges, and Lessons Learned, presented by David Siegel, is brought to you as part of Mobius Connect's Week of Webinar series. I'm Alexa Gruber, the media specialist for Mobius Connect, and I'll be your moderator for today's session. Just a quick note before we start, this webinar is being recorded, and you will be emailed a link with access to the on-demand version later. And if anyone has any questions throughout the webinar, you may type them in the Q&A panel on your screen anytime throughout the session. And at the end of it, David will be more than happy to answer your questions. Your questions will be answered on air anonymously, so no need to be worried about being called out. And if we do run out of time and we don't get to your question, David will reach out to you directly after the webinar to make sure that your questions are answered. All right, David, without further ado, I'm just going to cut straight to it and get you started with your presentation.
Yeah, thanks, Alexa, for the introduction. So this is David Siegel from Predictronics. I'm currently the CTO, and I have a background in predictive maintenance, in particular using machine learning techniques to apply it to predictive maintenance solutions. So I've been working at Predictronics for over 10 years, so I have a lot of experience in this field, as well as previous work at the university. And here today, we'll talk about how to apply machine learning for predictive maintenance, some of the best practices, the challenges, and then we'll get into some of the success stories and case studies in manufacturing, heavy industry, and utilities, and then some concluding remarks. So first, an overview, this, seeing where I'm coming from and what my perspectives are. And first, I like to start out with, why predictive maintenance? What value does it bring? And these are just some example numbers from our applications where we deployed it in a manufacturing space. So you look at predictive maintenance, you're thinking about, how to reduce unplanned downtime, optimize the preventive maintenance schedules, and even a few percent reduction in unplanned downtime can lead to, hundreds of thousands of dollars savings. So there's a really compelling business case in many circumstances for predictive maintenance solutions. And this is kind of our view of how to, develop and deploy these predictive maintenance solutions. Of course, there are variations on these various approaches, but we first start out by, selecting, more critical machines or equipment in a given manufacturing or heavy industry or process plant, whatever it may be, and really want to focus on the heavy hitters. So if you reduce these downtime, you'll see a significant savings. These are, really critical equipment in the shop floor or what have you. So we then think about what data we need to collecting the right data at the right time, at the right quality. And then from there, all the subsequent analysis steps, take place from, signal processing, outlier removal, really cleaning the data, and then maybe doing some segmentation to focus on a particular process step or operating, condition of the machine. And then we extract, features or patterns from that data, and then ultimately combine those patterns using machine learning for looking for departures from that normal condition or for diagnosis and so on. And we have this health index that is then tracked over time. And then ultimately, this solution is configured in our software or other people's software, and that is then implemented, and the data is coming in live and processing and determining the health condition of the machine, and then reporting and providing alerts ahead of time of any impending machine problems that are starting to develop. So with that in mind, there are, different ways to implement, and this is kind of a high level view of, starting with the machine layer, what machines are you monitoring? Is there existing data you can leverage upon? If so, you can, leverage that existing data, or in other ways, or maybe sensors that are part of the machine control system where you can use various protocols to then gather that data. But in many instances, the data that you need for predictive maintenance isn't available, so you have to add additional sensors and data acquisition devices to make that possible. Whether you're adding vibration, rotational speed, pressure, temperature, what have you, you need to add that additional instrumentation layer and then combine both data sources. And then once you have that data in place, you can then configure the analytics and deploy, in this case, our predictive maintenance solutions that are leveraging some of the machine learning, methods and techniques for data analysis. So that seems simple on paper. You have data coming in, you have all these advanced analytics. Why doesn't it not work all the time? Or what are the challenges that could come, could arise? And if you look at it, there are several challenges. And I think probably the one that's on the top is probably what I feel is the biggest challenge currently, is just the quality of data. A lot of times, data that has already historically been collected was maybe not naturally intended for predictive maintenance. Maybe it was more, someone just thought the data was there, they could, put it in a historian. It may have never really been intended for finding early symptoms of machine problems. So there's a lot of challenge in getting the right quality of data, including the sampling rate, how it's triggered, whether contextual information is captured, and also kind of marrying it or aligning it with maintenance records. That way you can kind of prove out the data if you have historical data and align it with past maintenance records to see if you can really find early indications of problems before an actual downtime event or failure occurred. Now, that's a big challenge right now. And then related to that is having sufficient data for building and evaluating these models, especially machine learning models. And that most cases, machines, thankfully, are relatively reliable. What that implies is that you don't have a lot of failure cases or failure patterns to learn from. And that does make it challenging to have sufficient data for building and evaluating the models. And usually you start out with more of a data that's representative of a baseline condition of the machine. Another challenge that you may not initially think about is that you want these solutions to work well, not day one or even 30, 90 days out or even 6 months out. You want it to work well for, a number of years, potentially the lifetime of the solution. So you have to think about how to maintain the accuracy of the solution. What if maintenance happens on the machine and the baseline behavior of the machine changes? Or what if the sensor location accidentally shifts or changes, or it falls off and they have to replace the sensor? So you want to have a way of maintaining the solution accuracy, updating the models, make sure that you have a way of easily updating things like thresholds or the baseline model, or even including more failure patterns to learn from. So you want to make sure that you have a way of maintaining this accuracy over time. The last part is that you have to think about the intended user of the solution. Is it a maintenance personnel or technician that's going to be in charge of repairing and performing maintenance on the machine? Is it an operator? Is it a maintenance manager? Is it a plant manager? Who's going to be using the system? And there may be multiple people using the system, but you have to think about who are the core users and what information they need to see, so the solution and the dashboard and the information presented to the user is actionable and they know how to interpret and make the right decisions from it. So yeah, I've mentioned data quality being a challenge, and just looking at it realistically, just from my experience, don't expect perfect data. Always expect that you're gonna have to do some pre-processing, some data cleaning. This is an example from a past project we did with predictive maintenance for marine diesel engines. And this is an example where the data was kind of scaled or normalized, this for the data privacy issues. But in general, this pressure was actually a negative value that's not realistic or not physically possible. So you have to think about different rules or simple methods to help clean and prepare the data to remove of clearly values that are not physically possible. So there could be outliers like this, or more contextual outliers, like you expect the temperature to be slowly rising. A really sudden shift in temperature wouldn't necessarily make sense. So a lot of those pre-processing steps are very helpful and can lead to a more reliable and more accurate predictive maintenance solution. And that was more just a pressure or more low frequency data. Fortunately for vibration, which is a very popular measurement for predictive maintenance, there are some established rules for judging whether the vibration signal is valid or not valid. It's still a little bit tricky in setting the appropriate threshold, but based on the overall RMS level, the number of consecutive points, that may be quantization related error, the distribution, the signal. There are several checks that you can make to determine whether the vibration signal is good or bad. And if it's bad, meaning it's not a proper measurement, that you cannot trust the signal and that you don't want to make a judgment on the machine health if the vibration signal is not valid. Maybe it's just a one-off thing, or it could mean that there is something wrong with the sensor itself or the cabling or how it was attached on the machinery. Maybe it became loose or something like that. So those were some of the challenges. Now let's think about the best practices. And as I mentioned, one of the challenges is maintaining the solution over time. And you have to be careful of this. You don't want to just, rest on your laurels. You have a good early detection, during maybe the initial piloting of this, solution, the first several months. That's great, but you have to think long term. I want the solution to be accurate and providing value for, several years, 5, maybe even 10 years. So I need to think about ways that I can update my solution easily. If a maintenance or repair action happens, maybe that changes the baseline of that machine. I want to update my model. Or maybe there's new assets that are coming in that I want to expand my solution for. So you really have to think about, how do I make my solution easily adaptable and reconfigurable to handle these changes that will naturally happen over time. Another important aspect is, as we were talking about earlier, about the user of the predictive maintenance solution. And I kind of think of it as a coach, a recommendation system. The final decision for most cases for predictive maintenance will still be made by a human. They'll still be interpreting this information and they'll still make the final call, but you want to make it easy for them. Like in this example, this is a robot that was developing a problem, and we'll actually get to this use case later on. You can see that the health was getting worse and worse. A prediction is saying in the next month they'll get to this red level. And that indication is saying that you have this month window to take action. And they actually took action on a weekend shift. We'll get to that details a little bit later. But you want to make the information actionable and easy to understand, so the maintenance or the operator knows what they have to do. And again, it's a recommendation. They still have the final call. It's not, I would say, autonomously doing maintenance. That's still something that's not very practical, and or where the current state of the art is in today's environment. And this is an example workflow. This is actually from a manufacturing customer. We were monitoring the machine tools, and one of the subsystems in the machine tool we were monitoring was the clamping system. It's a hydraulic clamp system. We were monitoring various pressures. So there's some data like timing information we were getting from the machine controller, but there's also this pressure data that was added to the system. And you can see that they got a report or alert in this case, and it showed them that the health was starting to trend. And also they could take a deeper dive to see this particular pressure related variable was having a very noticeable trend over time. And that will allow them to then investigate further and then schedule the maintenance before it leads to a more costly failure and downtime with this machine tool and its clamping system. So these are some lessons learned just from our experience and working in this field and deploying these predictive maintenance solutions that are leveraging machine learning. Is these are the 5. So first one is start small, in the sense that you want to prove it out. You don't want something that's the most complex machine in your factory. Of course, it would be a great win if you could prove it out there, but you want to start with more of a moderate case. And the reason why I say that is that you want to get the success. If it's very simple, you may not, people may counteract and say you didn't really need machine learning. You could have done it in a simpler manner. So more of a moderate case, but start small. And if you do, or if you're not successful, at least you can invest, millions of dollars in that type of solution. You want to start small. If you do fail, you want to learn from that and then take those lessons learned moving forward. And then the second point is that machine learning, can work quite well, but it's not, I would say, magic, or it can't work with data that is completely, not of poor quality. So there has to be some level of moderate quality in the data to work from. And of course, you can clean it up with outlier removal. But if, for example, if you're monitoring bearing health, you're not measuring vibration, you're not measuring temperature or motor current, you're measuring, maybe, something else, or it's very far away from the machine or the bearing location, it's not going to be able, the machine learning is not going to be able to just use that data that's completely irrelevant and make sense of it. So it has to have some relevancy and some correlation with the problem that you're trying to predict and prevent. And we already talked about a high value problem and not the most challenging. I think that's an important point, in that you want wins. This is still relatively new technology, or in the way that machine learning is being incorporated in predictive maintenance. Of course, condition-based maintenance has been around for a while, but the incorporation of more advanced analytics is still relatively new. People are going to have some doubts of whether it works, or they may have been, had some misfires or, poorly executed projects in the past. So you want to make sure that you choose something that has a high probability for success. And then the fourth one is that, as we mentioned, machine learning is not magic. you can incorporate domain knowledge. There's nothing that says that it has to be purely one way or the other. You can incorporate the knowledge you already know about the machine, what sensors would work, what frequency patterns may be related to these types of failures. Incorporate that as much as you can, and then combine it with the machine learning to help automate the recognition of various patterns or anomalies and so on. And then the fifth one is kind of integrating it into the user. So you want to make it where it's part of their daily or weekly routine, where they're using the software, they're understanding how to get value out of it. It's part of their work routine, and that way they're more likely to adopt it and continue using it. If it's something where they're not necessarily incorporating into their daily practices, the likelihood that they're going to be using it after a few months is quite low. So with that in mind, let's talk about the success stories. I know we talked about some challenges or lessons learned, but I like to show where it works. And these are numbers that you can find in the literature. So there are some, I think, references that we have here. We put them at the end of the slides. But the first one's actually the center that I actually worked at the university, the Center for Intelligent Maintenance Systems. We had primarily focused on the manufacturing sector, and there was an independent study by the National Science Foundation where they found that we had, based on the solutions that were deployed, it saved the manufacturing customers that we were working with, 847 million or so. So that was a huge amount. Now, one company, had saved 500 million. Others were maybe 5 or 10 million, various amounts. It depends on, what manufacturing they're doing, how much product they're making, and so on. But very, very successful use case. And then we had another one with Toyota with the prediction and prevention of the compressors. They had these surge issues, so predicting and preventing the surge. You can see there's a pretty significant cost savings that they're having yearly. And then some other examples in appliance manufacturing and aerospace manufacturing. And it's just looking at not just manufacturing, other industries. If you look at predictive maintenance, condition-based monitoring, that's been widely used in aviation, especially in the helicopter, health and usage monitoring systems, probably for over 15, 20 years now. And they reported 112 million savings in this aviation defense application, mostly based on vibration. A lot of it's vibration-based monitoring, also monitoring torque, and also looking at the uses of the equipment, not just the health based on the vibration data. It's a very successful example. And these are some additional ones in power generation with GE. And then Intel, also in their manufacturing facility, millions of dollars savings from these reported studies. So that should show you that when applied, it can work great. And we'll show you some of our examples that we've worked on. And the first one being in the automotive manufacturing sector, predictive monitoring of some key equipment, key machines in this wheel manufacturing plant. And if you look at this particular application, it's a very nice application because I would say it's more of a turnkey application. Their equipment, to be honest, was very old, 50, 40 years old. They had this roll forming equipment that made the rim of the wheels, and then the wheel spinner or flow forming machines that made the disc of the wheels. And then those two were the disc and the rim were then eventually welded together, and eventually they would make the final product. But these roll forming and wheel spinner equipment were very old, and it wasn't really feasible to obtain any data from the control system. It's very legacy control systems. All the data that we had to collect was from additional instrumentation that we added to these machines. So looking at adding vibration, position, rotational speed, pressure for their hydraulic systems, and so on. So we really had to add some additional instrumentation and hardware to make it possible for predictive maintenance. But they were really problematic machines because they were quite old. They were seeing a lot of failures and unplanned downtime due to their machines degrading and developing problems. So yeah, these are some example signals. This is actually for the wheel spinner. We're looking at vibration, 4 different locations, measurements of flow rate and pressure for more the hydraulic system. And that really provided a pretty good story of what was going on with the flow forming equipment. And there was a similar set of signals for the roll former machines, looking at vibration as well, but also position and RPM and so on. And these are some good examples of early detection. Now, this is an example where there was a particular problem developing with the rough roll. which is a part of the spinner equipment. You can see that its health was initially quite healthy in early March, and then kind of, March 5th, March 6th, is starting to develop a problem that's just leading to more and more unhealthy state. And they were able to receive this notification, take action before it got to a really severe state that would have caused the machine to stop production. In this case, there was a particular vibration frequency, a particular vibration band that was much higher than normal. So this early indication, several days ahead of time, allowed them to take action and prevent this failure from happening. This was kind of more later on in their use of this solution. Probably the earliest one, which really I'd say helped validate it for them, was this was part of the phase where we had just deployed the solution and they were getting used to using it, and they were kind of wanting to see the evidence that it worked. So they were still in the show me that it works, or I'm not going to believe it till I see it. And this was actually a problem that was developing on their spinner equipment. The same equipment is actually a problem with one of their bearings. And our solution, based on the machine learning and finding departures from the baseline data based on the vibration, pressure, and what have you, was showing, 10 days before the actual failure, on this January 24th date, there's a major problem. It's very clearly anomalous. The vibration is way out of normal of where it should be. The patterns are, very different than where it was originally. And then 5 days after that, you see right here, they're starting to notice not only is our solution saying there's a problem with the machine health, they're actually starting to notice quality issues, but they're not necessarily correlating it back to this machine health issue. And then finally, 5 days later, they have this big bearing failure, and it causes a month of downtime. And then after this, they were like, okay, we really need to start not just using the system, but taking action and believing it. They were thinking that this may have been a sensor issue, but that was obviously not the case here. So I think really successful implementation. There were several examples of those early detections. And, the one that really built their trust was that one that had that bearing failure. And, we could see it clearly having a problem 10 days before the failure. And they reported, with using the system, $200,000 in savings. And they've since then, expanded it. And it's now, deployed at another plant. And originally, the first plant we deployed was in Ohio. Then the second one was actually in Europe and Germany. So they're quite happy with this type of technology and the solution. Maybe as a side note, it wasn't mentioned here, but this was actually nominated for the Manufacturing Leadership Award for the use of machine learning and AI, and it won it, I think, a few years back. So again, was very well received when we summarized this information for the Manufacturing Leadership Awards. The second example is actually also in automotive manufacturing, but not using, I would say, vibration data, just leveraging the existing data from the robot's control system, looking at basically the motor current and position data from each axis of the robot to monitor the health of these robots. And this particular customer, they had 500 robots in their factory, automotive assembly, a lot of robots doing welding and assembly at that factory. And for them, 1 minute of downtime is very expensive. They're making the frames of the vehicle. So they're making a pretty big part of that vehicle. And for them, 1 minute of downtime is basically $10,000. And before the solution was deployed, they had 30 robot failures during production the year before. And on average, downtime for a robot failure is 30 minutes. So you can just do the simple, numbers, and you can see that, one failure cost them $300,000, and they had 30 of those. So you're looking at even just catching a few of these, even, say, for example, 50% of these we predict and prevent, we're looking at, millions of dollars savings. So, that's a pretty compelling business case to move forward with this type of solution. And obviously, you can't predict and prevent everything. That's another important point. Looking at robotics, there are things that are suitable for predictive maintenance that have wear out patterns that you could find early problems or early indications of, whether it be, gear backlash, worn belts, the motor brake failure that we'll see later on, bearing failure, and so on. Other ones, more electrical in nature, a cable failure, a dead battery. Those things may be more suited just for preventive maintenance. You're not going to solve everything with predictive maintenance. You have to, I would say, pick your battles, pick your wins that you think the solution is tailored for, And then you still need preventative maintenance. It's usually a combination of both that you'll get your, I'd say, your biggest bang for your buck if you think of it from that perspective. So with that in mind, we leverage the existing controller data from the robot. It's kind of learning the baseline behavior for each individual robot. Even though they're the same, I'd say, FANUC robots in this case, there's still a little bit, individual variation from one robot to the next. So it's kind of learning its individual baseline pattern. We're segmenting on a cycle by cycle basis. We're learning those patterns, and we're using that to kind of configure this algorithm or analysis method to determine how far it's departed from that normal behavior. And it's calculated this health index where 0 is healthy, 1 is warning, and 2 is more immediate action or immediate maintenance is needed. And we also had this prediction of where it's heading in the next weeks and months. So here's an example. This is actually a screenshot that you saw earlier, but I'll kind of go into a little bit more detail. So this particular robot, you can see that initially it was quite healthy. The health values were at 0. And then starting around September, it was getting worse and worse and worse. And then leading up to October, is kind of approaching or right at that warning level. And our prediction is saying if everything persists the way it's heading, it'll reach an unacceptable level of health in the next month or so. In addition, it's a 6-axis robot. The main contributor is axis 5. That's where you should go and look. That's where the problem is lying for this robot. That's the axis that's having issue. So they were a little bit conservative. They actually didn't wait till this month. They used this kind of forecasting window, and they're like, we have some time on a weekend shift in, I believe, early November, right around this time frame, and we can inspect the robot. In fact, it did have a bad axis, a bad motor brake on axis 5, and they were able to find that early on and fix it on a weekend shift and not interfere with production and basically solve it before it would have led to much more issues and production stoppages. What they were saying is that if it's left, unintended or, no maintenance is done at that state, it would have caused more position accuracy issues and collisions. Eventually, it would have caused a stoppage in production. So they were really happy that we were able to solve it before it got to that state. These are some additional examples. This is in the logistics industry. So a lot of conveyor belts, conveyor systems, monitoring the health of the motors and gearboxes as part of this conveyor system. And this one is a little bit shorter case study. We're just going to kind of get to the main concepts here. But this was a very, I'd say, vibration-based predictive maintenance application. We're looking at, vibration sensors on the motor. And because they're on the motor, we can also kind of sense issues that could happen with the gearbox and other parts that are downstream of the motor. We were also measuring the motor current to get more insight on the operation of the machine as well as for machine health. But it's a really successful use case. I'd say you're looking at rotating equipment. It's actually one that's still, we're still adding more machines. We're right now at 8 motor gearbox. There'll be 16 and by the end of this year, and hopefully a lot more for the upcoming year. But you can see in this example, initially it was very healthy, and then starting in November, it was getting worse and worse and worse, and the health value was way above the critical level for I'd say at least a month. And then they did this is again when they're starting building trust in the system. This was kind of our first early indication catch. It in fact did have a gearbox issue and failure. So with this solution, you can see that there was a month early indication, and that's really where you want to be. You don't want to be hours or even a day is probably not enough. You want to be several days, weeks, or even a month prior to the failure, and really at that point there at least should be an early indication that something's going wrong. Because if you show that something's going to fail and they inspect and they don't see anything wrong with the machine, they're not going to trust it. So you want to be at this early indication spot where there's still enough time to take action and not lead it to more of an unplanned failure. You want it to be more of a scheduled maintenance, and you kind of have this month to couple week opportunity window to catch it early and then take action before it leads to more of a functional related failure. So the next example is also more vibration based, which is again a very popular sensor signal for predictive maintenance. So it's not surprising that you're seeing a good deal of vibration related case studies. This one is for oil and gas industry, predictive monitoring of reciprocating pumps. In this example, we're looking at these reciprocating pumps. We're measuring vibration at a few locations. We're measuring pressure and flow, if I remember correctly. And for them, they wanted to do it at two different stages. They had this test bed, and they wanted to first validate the technology. Sometimes the validation happens in the field. For them, they were like, let's just make sure. We're going to induce some failures on the pump, some, seal and other related failures. We want to make sure it works. And then in parallel, we're also going to be monitoring some pumps in the field. And if we do catch a failure, great. If not, we'll at least know the solution works from those kind of seeded fault experiments that they were doing in a more controlled environment. And actually both were working well. So initially validation with the seeded faults, it was really showing good indication of the seal and other related failures. And then we were able to also find a problem that developed in the field as well for two of the reciprocating pumps that we're monitoring. So you look at, pumps in general, there's various types of pumps. This is not obviously a comprehensive list, but I think in general, I'd say vibration is probably the most important one. I think pressure and flow rate are also very useful as well. You can also look at the, for centrifugal pumps, you can look at the kind of the performance curve of the pump. That can be, some measure of health that you can, gather from that type of information. And the vibration can pick up a lot of, the, mechanical related faults, bearings, seals, things of that nature. And then cavitation, maybe also in higher frequency, you can also see with the vibration. So moving on to this particular case study, for these reciprocating pumps, we're looking at the vibration patterns, pressure patterns, and so on. And a lot of rich information was in the vibration data. We had this measure of, I wouldn't say rotational speed, I'd say the reciprocating speed or angle. And we could use that to kind of align the data based on the angle of what it was doing as it was kind of, reciprocating up and down. And with the vibration data that we're collecting, we could really look at the time and frequency patterns along the cycle, along, its movement, 360 degrees or up and down, for one cycle. And with that information, it was very rich to extract these kind of time and frequency patterns and then combine those into an index of how healthy that pump was over time. And for them, they also wanted to know not only the early indication that the pump was going bad and maybe what part of the vibration was contributing to that problem. They also wanted more of a diagnosis. Is it a seal failure? Is it a bearing failure? Is it cavitation? So we had kind of this, I'd say, image type of technique. We originally were using some machine learning neural networks, but that was overcomplicating it. And we could actually just do the same level of accuracy with more of this kind of matrix similarity method that was still using similar inputs, but a little bit more simplified method. So overall, you can see here that this particular time and frequency pattern was showing a really nice trend leading up to this failure. This was actually another issue, a sensor-related issue that they were also interested in knowing about, maybe less urgent than this particular leak-related event that they were really interested in getting early indication for. So they're really thankful that the system was in place. They could have received this early indication days ahead of their failure with this leak event for one of their reciprocating pumps. So I believe this is the last case study. It's also on pumps, not in the oil and gas industry, but in the water industry. And I think it's a nice example because it shows where predictive maintenance, we've seen a lot of examples where it's finding early indication of problems. It's used to then schedule maintenance in a more proactive manner, so it doesn't, result in unplanned downtime or unexpected failure. And that's, I'd say, the typical use case. But there are also issues that happen during installation, or maybe the maintenance is not done properly, and an issue can occur from the start or after maintenance. And if it's left unintended or unnoticed, it could actually lead to bigger problems down the road, eventually a bigger failure. So this is a good example of catching those installation issues. So we were working with pump OEM in the water industry. And for this kind of initial pilot study, we looked at focusing on 5 pumps. Let's see how it works in the field with some field data from the pumps. And they already had the data collection in place. It wasn't, I would say, the original waveform of the vibration, which is probably the most rich information, but they were doing a pretty good job of kind of capturing the summary information from the vibration, the overall magnitude, the peak to peak, some of the frequency of the main peaks and characteristics. So it was, I'd say, for a summary type of information, it was pretty good. I would say, obviously, the the raw data has more rich information, but I think it was pretty good for understanding their market and the data bandwidth and limitations there as well. So this was the flow chart. So we have this kind of summary information. It's a little bit noisy, because there are different vibration levels, different operating conditions that can happen. So using this kind of 1 hour sliding window really helps smooth things out. We then combine multiple indications from the vibration, as well as there was a temperature that we can compare with ambient. So we also look at the temperature rise, and we use kind of a month of baseline data to kind of learn the baseline behavior of these pumps. And then we apply this kind of multivariate algorithm based on kind of auto-associative type of model. We actually use more of a matrix formulation as compared to a auto-encoder or different types of neural networks that can kind of give you the same result, but sometimes a little bit more complicated. And then we configured our software to then show the results. This is a little bit more into detail of what was actually into the model. So we're using that 1 hour moving window. We're looking at XYZ vibration, also the temperature, and looking at some of the overall magnitude and peak ratio or other information. The peak ratio is actually the ratio of the peak at the 1x to 2x. So it's kind of a good indication for diagnosis of kind of helping determine whether it's maybe a misalignment or imbalance or what was going wrong from more of the mechanical side. Overall, very successful. As I was mentioning, or kind of alluding to, is that a lot of these problems were installation-related issues. They had a lot of, I'd say, cases where these new pumps that were installed in the field, they had these misalignment issues, and the health was really starting to, show right from the beginning that it was abnormal, and it would actually get worse over that course of the day. And what we're showing here, this is actually historical data to kind of prove it out. But with the system in place, they could know right from the get-go when they install it whether it was installed correctly, as opposed to having a field person come back, that time to drive there and set up everything and figure out what's going on. So that was really one example of how this solution could be used. And since they were relatively new pumps, we didn't see any other failures in the field, but you could see these kind of installation-related issues in this example here. And you can see there are certain features that are contributed. The RMS was obviously much higher, but it's also interesting that this peak, relationship between the 1x and the 2x peak, the peak at, the imbalance versus the misalignment, that ratio, was consistently, if you look at the 2x to 1x, it was a certain ratio that you would see only in that instance. So it gave us more confidence that it was really the alignment related issue, which in fact it was. This is the second example. They actually had more than one example. So they actually had 5 pumps, and two out of the 5 that we had selected had this issue early on. So it was quite interesting, and they could see this one was probably less severe than the previous one. So I think we still have 6 more before the Q&A. So I do want to highlight some concluding remarks. And first starting off with looking at the value that predictive maintenance solutions can bring. And of course, there's the caveat if applied correctly. So there's a lot of these challenges in terms of data quality, having sufficient amount of data, understanding, that the solution needs to be updated and kind of maintained over time. And then lastly, designing the solution for the end user in mind. Now, if you can overcome all those challenges or considerations, you can see that there's many successful stories. The ones that we showed here, the ones that we documented, maybe not in detail, but just from the literature on cost savings and value that were provided. You can see that when applied correctly, there's a lot of value that these solutions can bring. But the solutions are still, I'd say, not always overcome. And I think you have to think about it from even the problem formulation stage. When you're first looking at, considering a predictive maintenance solution, you really want to nail down what assets and machines you want to monitor, what is the amount of downtime they've had before. You really want to do that criticality analysis properly and define the business case, do all those things well. And a lot of the rest of the technology steps, technical steps can happen quite nicely. So I think a lot of times we see these solutions not being successful. A lot of times the issues really aren't in the later steps, and the later steps are maybe trying to compensate for steps at the beginning that you didn't do correctly. So if you try to set up everything right from the problem formulation step well, a lot of the other things can work quite nicely. And yeah, I think we looked at, maintaining the solution over time. But it's also difficult, I would say, to how to make sure that the solution has the ability to be updated and learned over time. But also, maybe it's not mentioned here, but how do you measure success? So we've talked about, we have these early indications. Someone did maintenance proactively and prevented a failure. You have to have a way of documenting and quantifying those early catches. You have to then quantify how much savings this would have provided, because you don't necessarily know how catastrophic or how much downtime the failure would have caused. You can make some assumptions based on some historical data, but I think it's important to consider how to maintain the solution, but also how to measure success. How do you know how much value the solution is even providing? And yeah, I think we've looked at some of the applications, especially in manufacturing, where you're looking at, I'm mentioning the use of baseline data and using that to kind of learn over time, use to train our models, and, machine learning models. You may be wondering, I'm not mentioning a lot about supervised machine learning, which I think does have its value, but it's challenging to apply for a lot of these predictive maintenance applications because you need past examples of failures, and those are relatively rare because the equipment in general has decent reliability. Of course, if it's perfect reliability, there'd be no need for this predictive maintenance type of technology. But that they do experience failures, but it's not like they're happening every day or even every month. Maybe every few months, especially if you have a large number of a fleet of assets, and the amount of data that you need to train these supervised models may be difficult initially, especially at the start. So I think that's all I have. Yeah, maybe I'll stop here to see if there's any questions. And these are just our references. I'll stop here.
Perfect. Thank you so much, David, for that presentation. We do actually have quite a few questions that came in. So someone had asked, how do you detect electric discharge symptoms in VFD motors by vibration analysis?
Yeah, that's a really tough question. Actually, I haven't worked on that personally. I guess I'll be honest. I may have to look back and research. That may be one I have to get back to you on how we would do it. Now, of course, the starting point would be looking at, how others have looked at those electric discharge, issues with, variable frequency drives. But yeah, I haven't actually personally worked on it myself. So I may be something I have to research after this call.
Okay, perfect. And another question, how do you detect data drift? For example, say a quality control application. Who decides when the model needs to be retrained, the line operator, or how do they bring the attention of the data scientists?
Yeah, this is an excellent question. And yeah, it wasn't, I would say, specifically mentioned in my slides. They were a little bit more predictive maintenance focused, but we actually do spend, I would say, 70% of our, work is on predictive maintenance, and other, I'd say 30% is on predictive quality. And a lot of times you're right, you do see these, I'd say slow drifts over time, whether it be in, for example, semiconductor manufacturing or, chemicals industry or glass manufacturing. One way of doing it is this: knowing, if you have historical data, you may know that this is possible. And actually, one semiconductor manufacturing application we had worked on previously, we actually had a model that slowly updates over time. It's kind of already baked into the solution. The one nice attribute about that is that the ability for the model to update is already part of the solution that's originally configured. The other part that we do, especially for both predictive maintenance and quality, is just having a way within the software to allow someone to select a new period for training. That does help. Now, going back to your original point of how do you know, this requires both, process experts along with the data science to, review the data and the software. I think there are some checks that you can do. It depends on the model too. Like if you're looking at, more of a, whether the quality is good or bad, kind of more of a binary decision. If you have a way of, maybe you're actually measuring the quality, once per batch. You could, if you have a ground truth, you can actually look at the accuracy over time. Obviously, if that's departing from where it should be or where it was originally, that would be a sign that you need to refresh the model. And same thing with regression. it's a little bit more challenging if you don't have that ground truth. It then becomes more of I say a more judgment call based on the review of the data. So those are just my insights. Of course, there's probably a more detailed discussion that we could do on that subject alone.
Right. Well, I mean, you will get all these questions, so you can probably go into more detail if you'd like later with them. Another question, what is a surge map?
So I think this question, if I understood it correctly, was what was a surge map?
Yes.
And this was related to the compressor case study, which we actually didn't go into detail. This was with Toyota. We had worked on a project at their manufacturing facility in Kentucky, which our offices are in Cincinnati, Ohio, which is pretty close by. And they were looking at the predicting and preventing these compressor surges. And there's a kind of a what they call a recommended region to operate based on I believe it's pressure and flow rate for the compressor, and there's kind of a surge line and recommended region from the manufacturer, and they were, I mean, that's what the control system is based on, and what we found is that there are other factors like ambient conditions, other things. They were actually still experiencing these surges before our project got started, and originally they were looking at a little bit going off topic. They were actually looking at predicting and preventing these surges. They weren't actually looking at the surge map and the pressure and flow rate. They were looking at originally using vibration to predict and prevent. They're actually looking at bearing failure. So the surges were causing these premature bearing failures. So looking at vibration. And after more discussions with them during the project, we were finding that the surges were the root cause. And then we looked at, there was the original, this region and the surge map where you could operate and it'd be safe, but it wasn't necessarily considering all the factors. So we then built this kind of classification algorithm. Actually, we use support vector machines, and based on the pressure and flow rate and ambient conditions, we were able to find a more defined and better region. So when we did quickly detect that a surge was about to happen, it was actually kind of more embedded solution. It would feed back into their control system, and they would actually adjust the inlet guide vanes to actually move it to maybe a slightly lower energy efficiency region, but actually prevent the surge from happening. So they actually implemented that, and it was very successful. I think you saw the cost savings of several million per year, and that's a lot of it's attributed to them just not having any of these surge related failures since that was deployed. So it's been a really good use case. But yeah, maybe that'll be another one that I can go into more detailed when I review the questions and send back my feedback.
Perfect. Another question. Can you explain the difference between a neutral net and a matrix formulation?
Right. So I mentioned, I didn't want to get into the weeds of individual machine learning algorithms, and there's many different types of neural networks. There's classification algorithms, there's regression algorithms, different types of supervised regression, supervised machine learning algorithms where neural networks are used, and also last 10 years or so, there's been a lot of popularity in more layers, more deeper, what they call deeper neural networks or deep learning. So with that, all that being said, the two algorithms I was comparing with, or I would say more in the class of auto-associative type of models, which may not mean anything just based on the name, but it means you're looking at the relationship in the data. Like, for example, if pressure goes up, does temperature also go up and things like that. So you're looking at just the relationship in the data. It's more of a, you can kind of a more unsupervised, or just learning the relationship in the data, the correlation. And we've used a few different methods. One of the popular ones for kind of learning this kind of correlation or relationship in the data is what they call an autoencoder. It's kind of this learning, you don't have an output. The inputs and outputs are the same. And that autoencoder, or kind of the original, back in the 90s, the auto-associative neural network was kind of a popular type of neural network for that purpose. And then, different types of autoencoders more recently. And that's the neural network formulation. So once you train it, it just kind of learns from the sensor data and kind of predicts what the sensor value should be, and you can compare it to the actual, or predicts what the feature value should be to the actual. So that's the neural network version. Now, also in the 90s and early 2000s, or around relatively that time, and maybe even before then, there's similar methods that are more based on matrix formulation. So the one that we are using, auto-associative kernel regression, you don't need to train a neural network. You basically, the training is the matrix itself. It's more based on how similar the data is. It's more based on distance calculations and kind of that similarity calculations. That's one that we've used. There's others, I'd say, very similar in concept. But yeah, that's the distinction. And again, I think this would be a good one where I could, in the Q&A, feedback, when I send those over, I can probably provide some links or papers for those that are a little bit interested in reading more if they're interested.
Wonderful. Okay, so this is your last question, David. What tools can you recommend for monitoring data drift and the curation of the customer's models?
Right. So I may be honest here. I'm not sure if there's, I'd say, off-the-shelf tools or software that are 100% focused on that particular issue of data drift and model accuracy. So I think with that being said, I think, again, you would look at, first, if you have ground truth, look at your model accuracy over time. That would be good indications of when a model refresh is needed. But that threshold of what accuracy is acceptable would also vary from each application. For some applications where, maybe you're trying to predict a certain output variable, maybe it's, a particular critical dimension or something of that sort, that may vary by application, but they may have a certain, recommended range to stay within. And if your model is not meeting that accuracy over time, that would be a good idea of when to refresh. And then more if it's a quality application, you're looking at good versus bad, there may be a certain level of accuracy that you may need to focus on. Usually for quality applications, I would say there's usually a preference to have more sensitivity and allow a little bit larger false alarm rate, which doesn't sound intuitive, but if you think about it, from a quality application, you don't want any bad quality to go through. You're trying to catch as much as you can. Hopefully nothing goes through, or you want to really, reduce that, from a data science term, recall rate or true detection rate. You really want to catch all of them you can, but false alarm rate can be a little bit higher. So your, I guess, so to speak, precision, from that data science term, could be a little bit lower. So you would probably have to have a defined metric that you're trying to track, that you want to measure. But besides that, from an accuracy standpoint, obviously you could look at, windows over time, look at the distribution of data, see how that is changing. Also, if you are, for example, that semiconductor application where we're, training a model in a moving window, you could actually look at your coefficients in your model or other aspects of the model, see how much that is changing. There are other ways of updating models over time. I know for a regression application, we were doing kind of a Kalman filter, or there's other ways of kind of learning from the data and updating the regression models over time. So there's various ways. I would say, to my knowledge, although I'll definitely look at it, when we review the questions, there may be available tools I'm just not familiar with, but I don't think there is, or at least not to my knowledge. So I think there are methods. And, for example, our software may have some methods for dealing with it, but there's not a specific tool or off-the-shelf software that just looks at process drift and when to update models or when to refresh models, unfortunately.
All right. Well, thank you, David, for all of your answers. And if anyone did have any more questions for David, please keep putting them in the Q&A panel on your screen, and we will send all of your questions over to David after this webinar for him to answer you personally. And thank you, David, so much for this presentation. Is there anything else that you'd like to add?
No, it's great to have the opportunity to share our work, and I'm looking forward to any questions or follow-up. Yeah, it's great to meet everyone virtually, and I appreciate the opportunity.
Wonderful. Thank you so much. And for all of our WOW attendees, we would like to thank you guys as well. We are pleased to provide our WOW 11 attendees with 50% off your conference pass to the CBM and Reliability live training conferences. There's one happening in Mexico in August and one happening in Australia in November. You can use the code WOW50 and reserve your seat to take advantage of this discount. These events will include certification training opportunities, hands-on workshops, and case study sessions. You can visit MobiusConnectConference.com to learn more about these live and in-person events. You can also find the link to register in the follow-up email after this webinar. Thank you again, David, so much for your time in this amazing presentation. All of our attendees, I'm sure, had a great time and loved you answering their questions. And on behalf of the entire team at Mobius Connect, thank you to the audience again. And coming up next after this webinar, we have Predictive Analytics, Taking Asset Condition Monitoring to Another Level, presented by Taha bin Mahmood. It's today at 3 o'clock Eastern. And if you haven't signed up already and would like to attend, you can just go into the Attendee Hub and join the session from there. And just as a quick reminder, please look out for an email from us containing the on-demand version of this session and your certificate of attendance. And if you are interested in engaging with other industry professionals or would like to participate in the industry's live feed and forums on Mobius Connect, you can visit MobiusConnect.com to create your free profile, and be sure to follow us on social media at Mobius Connect to stay up to date with the latest community happenings. If you have any questions, you can please email the Mobius Connect team at info@MobiusConnect.com. Thanks again for joining us, everyone. Have a great day. Please stay safe, and we'll see you next time.